Hello, in this video we're going to look at a question on collisions that is very interesting because it highlights one of the most fundamental things about collisions, and that's that we look at momentum first. So we know in a collision that momentum is always conserved, but we don't know if the kinetic energy is or not. So energy, obviously that has to be conserved as well, but we don't know if we've got the kinetic energy being transferred to other energy stores in this or not. So momentum, we don't have that problem. And I see people when they start working in collisions making the same mistake on this question. So I'll go through it first of all, how it should be done, and then we can have a look at sort of common mistakes that get made with this. So we've got a projectile of mass 0.2 kilograms. That's this, as you like, looks like a little bullet here that's being fired at a speed of 122 meters per second into a ball of mass 12 kilograms, hanging on a massless string, fixed length, and then it hits towards the center of the ball, and it stops inside the ball. So they're going to become one object once they've come into contact with each other. So we need to go in first of all because he wants to know, well, what's the maximum height that the ball is going to get to with a projectile inside. So we need to do conservation of momentum first of all, because then we don't have to think about elastic collisions, inelastic collisions, and all of that. I mean, this has to be an inelastic collision because anytime the two objects combine, it is going to be an inelastic collision. But then we've got the issue, we don't know how to quantify that. So let's start with conservation of momentum. So beforehand, we've got momentum of 122 times 0.2. So let's just make that a fifth instead. And then that is going to be equal to the momentum that we've got afterwards. So in this case, we've now got 12.2 so 12 and a fifth is our mass, and we're multiplying that by V. Right, so let's get rid of all of these fifths then. So we multiply everything by 5 in all of this. So we've got 122 is going to be equal to 61 V. V is 122 over 61. Well, isn't that handy? So V is now 2 meters per second. So it's dropped off considerably, as you would imagine. Right, so we've got all of that worked out. We know what the new V is. So now we can do our conservation of energy because we've got the velocity after the combination of the two objects. So we can say that a half times m, which is our 61 over 5, times v squared times 4, that is going to be equal to m 61 over 5 gh. So we can cancel lots of things here. That becomes a 2. So h is going to be equal to 2 divided by g. So it's not going very far up, but that is the height, 2 over g meters. Right, what I see people often doing wrong with this is they go straight in for conservation of energy. So if we're going to do this incorrectly and you go straight for conservation of energy, then you'll say, well, a half mv squared is what we've got at the start. So that's a half times a fifth times 122 squared. And that is going to be equal to our final mgh. And our final mgh is the 61 over 5 times g times h. And then they try and figure out all of this. So let's cancel those fifths. We can get rid of that, and that. And then we're left with 122 over g is our h. So that gives us h equals 122 over g. So we've got a massive increase in h there. It's 60 times bigger than what we had when we start off with conservation of momentum. So yeah, there has to be a lot of energy loss in this. I mean, this is an inelastic collision, so we are losing kinetic energy when the objects combine. But it goes to show the importance here of doing conservation of momentum first. And we always need to do this. We know that conservation of momentum, always fine. It's always going to work when we're looking at collisions, whereas the conservation of energy approach isn't. So we need to reserve conservation of energy for between the collisions, unless we know that it's elastic.